Well, in this lecture, we shall prove the Jensen's inequality. In the previous lecture, we had discussed something about certain things about the convex function. So let's first recall a test of convexity. We had done a test of convexity that if the second derivative of a function is positive, if f double dash of x is greater than 0 or greater or equal to 0 for all x belonging to the interval I, then f of x is convex on I. Is convex on I. And similarly, if f double dash of x is less than or equal to 0 for all x belonging to I, then f of x is concave on I. Concave on I. And we had applied this test of convexity and concavity on certain functions. So here we shall recall one such function. One such function was the function for example, we had done it for the function log of x, which we had proved that it was a concave function. So then f double dash of x is actually equal to -1 divided by x squared, and the domain of this function is x belonging to the interval 0 to infinity. So now this function is always less than 0, and so f of x is concave. Okay, this was just a recapitulation of the previous test of concavity and convexity. Now in this lecture we shall take up the Jensen's inequality and prove it. So we shall do it in the form of a theorem. This is Jensen's inequality. Jensen's inequality. Well, this Jensen's inequality tells us that let I be an interval. Let I be an interval and f from I into R be a convex function. F from I into R be a convex function. Be a convex function. Suppose x1, x2, xn are points in I, and lambda 1, lambda 2, so on, lambda n are the real numbers which belong to the be real numbers. Let these be the real numbers in the interval 0, 1, such that this lambda 1 plus lambda 2 plus so on plus lambda n is equal to 1. So then the Jensen's inequality tells us that then this f of summation I running from 1 to n lambda I into xi, this is always less than or equal to summation I running from 1 to n lambda I f of xi. So this is actually a generalized version of how we had defined a convex function. So let's recall it again here. We had defined the function to be convex if it satisfies this kind of an inequality, f of lambda x plus 1 minus lambda into y is less than or equal to lambda f of x plus 1 minus lambda into f of y. Then such a function was called convex. In fact, here we are choosing this lambda and 1 minus lambda. These two real numbers actually satisfy lambda plus 1 minus lambda is equal to 1. So if we have any two real numbers, in any two positive real numbers which satisfy alpha plus beta is equal to 1, then we always have for a convex function that f of alpha x plus f of beta plus beta y is less or equal to alpha f of x plus beta f of y. Then we will call such a function as convex function. And now here we have a generalization of such a concept. So now let's take up a proof. Now we shall use induction on I. We use induction on N. Now in fact, we will start the induction from N equal to 2 for N is equal to 2, because for N equal to 1, we will have nothing to prove. For N equal to 2, this is precisely the definition of a convex function. This is precisely the definition of the convex function. Because in this case, when we have only two real numbers, because in this case we have, because this f of this lambda 1 x1 plus lambda 2 x2 is less than or equal to lambda 1 f of x1 plus lambda 2 f of x2, where lambda 1 plus lambda 2 is equal to 1. This will be true because f is a convex function, so it will always satisfy this kind of an inequality. So therefore, the result is true for n equal to 2. So we suppose the inequality is true. Suppose the inequality is true for all k less than n. For all k less than n. So that's what we are assuming. That is for k less than n. For k less than n, if x1, x2, xk are the points, if these are the points in the interval I, and lambda 1, lambda 2, lambda k, suppose they are the real numbers in the interval 0, 1, such that their sum is equal to 1.
It's 9 o'clock.
Plus lambda k is equal to 1. Then we have the inequality, then summation f of summation I running from 1 to k lambda I xi. This is less than or equal to summation I running from 1 to k lambda I f of xi. So this is what we mean by assuming that the result is true for all k less than n. So in fact, we are here assuming the induction hypothesis that the result is true for all integers less than n. So that the result is true for up to n minus 1. Now, finally, we have to prove that the result is true if we have n pointers in the interval I and n real numbers in the interval 0, 1 whose sum is equal to 1, then we need to prove the inequality. So now consider, okay, so now consider any n pointers consider any n points x1, x2, xn in the interval I consider any n points in the interval I and real numbers lambda 1, lambda 2, lambda n in 0, 1 such that lambda 1 plus lambda 2 plus lambda n is equal to 1. So now we have assumed these n points and these n real numbers whose sum is equal to 1. Then we will prove the inequality is true. For that thing, we have to use the induction hypothesis somewhere, and for that, using the induction hypothesis, we will define some construction. So here we put y1 is equal to summation I running from 1 to n minus 1 lambda I xi whole divided by summation I running from 1 to n minus 1 lambda I. We define y2 is equal to xn. We define alpha 1 is equal to summation I running from 1 to n minus 1 lambda I. So in fact, we can see that this alpha 1 is the denominator of this y1, and we define alpha 2 is equal to lambda n. Then we observe that then alpha 1 plus alpha 2, this is equal to summation I running from 1 to n minus 1 lambda I, which is the value of alpha 1 here, then plus lambda alpha 2 is equal to lambda n. So this is equal to lambda 1 plus lambda 2 plus lambda n, and this is equal to 1. And so we have this alpha 2 is equal to 1 minus alpha 1. And also the points, and also the points y1 and y2 are in the interval I, are in the interval I. Okay, so then, so you now using the convexity of F. Now using the convexity of F. Now using the convexity of F for the scalars, alpha 1 and alpha 2, we have f of alpha 1 y1 plus alpha 2 y2. This is can in fact be written like f of alpha 1 y1 plus 1 minus alpha 1 y2. Now here we can use the basic definition of convexity. This is less than or equal to alpha 1 f of y1 plus 1 minus alpha 1 f of y2. But now this is actually equal to alpha 1 f of y1 plus now 1 minus alpha 1 is equal to alpha 2. So this alpha 2 f of y2. Now again here we can use the value of this alpha 2 and y2. So this can also be written as this alpha 1 f of y1 plus now alpha 2 is equal to lambda n and y2 is equal to xn. Alpha 2 is equal to lambda n and y2 is equal to xn. So this is lambda n f of xn. Now, if we are able to prove, so in fact, in the left-hand side and also this alpha y1 y1 plus alpha 2 y2. Now this is equal to, now as we have put this alpha 1 is equal to summation I running from 1 to n minus 1 lambda I, and this y1 is equal to, y1 has this value, this y1 is equal to summation I running from 1 to n minus 1 lambda I xi divided by summation I running from 1 to n minus 1 lambda I. So this is alpha 1 y1, then plus alpha 2 is equal to lambda n and y2 is equal to xn. So now here we can see that we can cancel out these two terms. So this is summation I running from 1 to n lambda I into xi. So therefore, this alpha 1 y1 plus alpha 2 y2 is summation lambda I xi. So therefore, if we can somehow prove that, so actually this inequality, so we obtain from this inequality, so we obtain f of summation I running from 1 to n lambda I xi. This is less than or equal to alpha 1 f of y1 plus lambda n f of xn. So therefore, actually our proof is complete. And if we are able to prove that this alpha 1 f of y1 is the remaining part of our inequality. So now in fact we can write this inequality is equal to, this is lambda 1 f of x1 plus so on plus lambda n minus 1 f of xn minus 1 plus the last term is lambda n f of xn. So now we can see that what we have obtained, look at this, these n minus 1 terms and this last term lambda n f of xn. So here we have this last term lambda n f of xn, but the first n minus 1 terms, in place of those first n minus 1 terms, we have alpha 1 f of y1. So now if we can somehow prove that this alpha 1 f of y1 is equal to this n minus sum of these n minus 1 terms, or that is less than or equal to the sum of these n minus 1 terms, then we are done with the proof. So the only thing that we now need to prove is that this f of y1 or alpha 1 f of y1 is either less or equal to this thing, or it is equal to this thing. So now let's call this equation some name. Let's call this equation as equation number 1. Now from this equation number 1, we will compute the value of this f of y1. So now in order to complete the proof, so in order to complete the proof, we consider f of y1. Okay, now let's see what we will do with this f of y1. So we have f of y1. Now this is equal to f of, now let's substitute the value of y1. This is summation I running from 1 to n minus 1 lambda I xi divided by summation I running from 1 to n minus 1 lambda I. And we will prove that this is less or equal to that n minus 1 terms, or it is equal to those n minus 1 terms. And now for this thing, now define mu L. This is equal to lambda L divided by summation I running from 1 to n minus 1 lambda I. And where the range of L is 1 less than or equal to L less than or equal to n minus 1. So in fact, we have now actually defined n minus 1 new constants. Then these constants share this kind of a property. Then mu1 plus mu2 plus so on plus mu n minus 1 is equal to, in fact, this is equal to 1. So let's prove it a little bit how this is equal to 1. So in fact, this is equal to, or we will write this equal to, now the value of mu1 is lambda 1 divided by summation I running from 1 to n minus 1 lambda I, then plus mu2 is lambda 2 divided by summation I running from 1 to n minus 1 lambda I, then plus so on. This is lambda n minus 1 divided by summation I running from 1 to n minus 1 lambda I. So here we have the sum of n minus 1 terms, and the numerator is lambda 1, lambda 2, lambda n minus 1. And the denominator is this summation I from 1 to n minus 1 lambda I. So the numerator and the denominator are same. So therefore this quantity is equal to 1. So therefore we have defined these n minus 1 real numbers, which are in fact all positive because they are defined for the positive real numbers only. So their sum is equal to 1. Now we will use the convexity of the function f for these n minus 1 scalars. So then by convexity, of the function f, we have this f of mu1 we have this f of mu1 x1 plus mu2 x2 plus so on plus mu n minus 1 xn minus 1. Now, since the result is true for all real numbers k which are less than n, so in fact it's also assumed to be true for n minus 1. In fact, it is true for all real numbers up to n minus 1. So therefore it is the convexity of f can be used on these n minus 1 scalars and these n minus 1 pointers from the interval I. So therefore we have this is less than or equal to mu1 f of x1 plus mu2 f of x2 plus so on plus mu n minus 1 f of x n minus 1. Okay, so therefore thus f of y1. So now actually we need to compute the value of f of y1. Now this f of y1 is equal to f of. Now let's see what is the value of y1. So this f of y1 is this quantity. Now in the numerator, we will expand this thing and we will write the denominator same everywhere. So this is lambda 1 x1 divided by summation I running from 1 to n minus 1 lambda I. then plus the second term is lambda 2 x2 divided by summation I running from 1 to n minus 1 I, then plus so on, plus lambda n minus 1 x n minus 1 whole divided by summation I running from 1 to n minus 1 lambda I. Now we can simplify it like this summation f of, now this is lambda 1 divided by summation I running from 1 to n minus 1 lambda I into x1, then plus lambda 2 divided by summation I running from 1 to n minus 1 lambda I into x2, then plus so on, then lambda n minus 1 by summation I running from 1 to n minus 1 lambda I into x n minus 1. And now we can see that these scalars are actually, this first scalar is mu1, the second scalar is mu2, and this n minus 1 scalar is mu n minus 1. So this is f of mu1 x1 plus mu2 x2 plus so on plus mu n minus 1 x n minus 1. But by induction hypothesis, we know that this is less than or equal to mu1 f of x1 plus mu2 f of x2 plus so on plus mu n minus 1 f of x n minus 1. So here we have used the convexity, and we have proved that f of y1 is less or equal to mu1 f of x1 mu2 f of x2 plus mu n f of xn. But now again we can use the values of these mu i's. So this actually equal to summation, or we can write this in the compact form. This is summation I running from 1 to n minus 1 mu I f of xi. Now let's substitute the value of mu I. This is summation I running from 1 to n minus 1. Now mu I was defined as, this is lambda I whole divided by summation I running from 1 to n minus 1 lambda I, and now here we have f of xi. But now this denominator, summation I from 1 to n minus 1 lambda I, this was defined to be the value of alpha 1. So this was alpha 1 here. Therefore, we can write this equal summation I running from 1 to n minus 1 lambda I f of xi and whole divided by alpha 1, where alpha 1 is actually the value of summation I running from 1 to n minus 1 lambda I. So now let's call this as equation number 2. So now let's substitute this equation number 2 in equation number 1. Now using equation 2 in equation 1, we have the left hand side of that equation was f of summation I running from 1 to n lambda I f lambda I into xi, lambda I into xi, and now this less or equal to, now the first term was alpha 1 f of y1, but now f of y1 has a value in like this, so it is f of y1 is equal to summation I running from 1 to n minus 1 lambda I f of xi, lambda I f of xi whole divided by alpha 1, then plus alpha 2 that was equal to lambda n, and here we have f of xi. So now we can cancel out this alpha 1 and alpha 1, So this is equal to summation I running from 1 to n minus 1 lambda I f of xi plus lambda n f of xi. So now combining these two terms together, we get this is summation I running from 1 to n minus 1. So this I running from 1 to n now. I running from 1 to n lambda I f of xi. So this completes the proof. So this was the Jensen's inequality on convex functions. In fact, this was a generalized definition of a convex function. So let's recall some basic things. A convex function was defined in this way: f of lambda x plus 1 minus lambda y is less or equal to this thing. And now the Jensen's inequality, if we have a convex combination, of pointers, that is lambda 1, lambda 2, lambda, and sum is equal to 1, then f of summation lambda I xi is less or equal to summation lambda I f of xi. And we used the induction for the proof of this theorem. For n equal to 2, the result is true by the definition of the convexity of the function f. And then we assumed the result is true for all natural numbers which are less than n. And then we prove the result directly for the natural number n.